In this video, we're going to take a look at matrices and systems of equations. Let's start with a matrix equation. Let's say we've got a matrix consisting of numbers multiplied by a matrix containing variables, and let's say that's equal to a matrix containing numbers. Now, if we multiply out the left-hand side, let's circle the rows of the first matrix and circle any columns in the second matrix. And to build this product, we're going to be doing some dot products. So our row 1, column 1 entry is going to come from taking the first row of the first matrix, dotted with the first column of the second matrix, and our dot product is going to look like 2 times x plus 3 times y. And since our second matrix here only has one column, that's the end of the first row, and we can now go into the second row. So we'll take the second row dotted with the first column, and we'll get 3x plus 4y. So that gives us a 2 by 1 matrix on the left-hand side. And this left side here is still equal to the matrix 19, 25. Now, a matrix equation like this really gives us a couple of different pieces of information. In order for these matrices to be equal, well, the row 1, column 1 entries have to be equal. So 2x plus 3y must equal 19. And the entries in the second row must be equal as well. So 3x plus 4y must equal 25. So in other words, this original matrix equation that we saw at the beginning really represents a system of equations. So the matrix equation AX equals B represents a coefficient matrix. So in our example here, our coefficient matrix was just this matrix here that contains the numbers or coefficients. It was 2, 3, 3, 4. X represents the variable matrix. So in our example here, the variable matrix contained the variables x, y. And on the right side here, B, that's a matrix that just contains our constants. So let's say matrix of constants on the right-hand side. And that, in our example, was the matrix 19, 25. So this expression here, AX equal B, that's just a general way of writing down a matrix equation, just like we had in our first example. And we've seen that AX equals B really represents a system of equations. Now let's say we've got a matrix equation, AX equals B, and we're going to now think back to some of our properties of matrices. If A happens to have an inverse, so in other words, if A inverse exists, what we can do is multiply the left side by A inverse, and at the same time multiply the right side by A inverse. And if we're going to do this, it's important that we put the A inverse on the left of the two different sides of the equation. Because remember, when we're multiplying with matrices, the order in which we multiply is important. So we really need to have A inverse B here and not the other way around. Okay, so if A inverse exists, we can come up with this new equation here. If AX was equal to B, then A inverse times AX is going to equal A inverse times B. And remember that A inverse is the matrix that undoes A. So when we multiply A inverse times A, we are getting the identity matrix. In other words, the identity matrix times X is equal to A inverse times B. And if we think back to our properties of the identity matrix, we said that when you take the identity matrix and multiply it by any matrix, you get that original matrix back. So this left side is really equal to x. And we're getting the little equation, x equals A inverse times b. So when we say that x is equal to A inverse times b, what we're really doing is we're giving a formula for x and y. In other words, we are solving for x and y. So let's summarize this idea. If the inverse matrix, A inverse, exists, then the system of equations ax equals b has a solution given by x equals A inverse b. So let's see if we can use this fact to solve the system. Typical example would look like this. The question would say, solve the system using the inverse matrix, A inverse, and then let's say we've got a little system of equations. So first step will be to write this system as a matrix equation. We want to write it in the form AX equals B. So if we think back to our first example, A was the matrix that contained all the coefficients. So we're just going to pull out these coefficients in the order in which they appeared in the system. So coefficients of x and y from our first equation, coefficients of x and y from our second equation. X represents a matrix of variables, and the variables are always written vertically just to make sure that this matrix multiplication is going to be possible. We write down the variables in the order they were given in the equations, so x and y. And this was equal to b. B was our matrix containing the constants, and we're just going to write down those constants vertically in the order in which they were presented in the system. So there is the matrix representation of our system. Now the fact that we just discussed said that provided that A inverse exists, the solution to this system looks like x equals A inverse times b. So to solve the system then, what we'll have to do is find A inverse, and once we've got it, we can calculate A inverse times b. So let's think back to how we find the inverse of a 2 by 2 matrix. Well, first thing we need to do is calculate the determinant of our matrix. So if we look back up here at A, the way we calculate the determinant is we take AD minus BC. So we're going to go 5 times 1 minus negative 3 times 2, and that gives us 11. That determinant is not equal to 0, so that confirms that A inverse exists. And if we think back to our formula, we have to go 1 over the determinant of our matrix times the following matrix. So the entries on the main diagonal are going to swap position. The A and the D swap position, and the off-diagonal entries are going to change sign. So the negative 3 will become a 3, the 2 will become a negative 2. So there's A inverse. Now to finish the problem, we're going to go back to our idea here that to solve the system, the solution looks like x equals A inverse times b. X was the matrix that contains our variables. So the matrix xy is equal to A inverse. We'll copy that out again. Times the matrix B. And looking back at our original matrix equation here, B was just the matrix on the right-hand side that contained the constants. So negative 34, 4. All right, so all we have to do to finish up is to go through this matrix multiplication. So generally, I find it a little bit easier if we do the actual multiplication first, And let's just leave that 1 over 11 out in front for now. So to do our multiplication, let's circle the rows of our first matrix, circle any columns in our second matrix, and we can build our dot products. Well, our first dot product is going to look like 1 times negative 34 plus 3 times 4. So that gives us negative 22. And in our second row, we get negative 2 times negative 34 plus 5 times 4. So that gives us 88. Last thing we need to remember here is what it means if we have a number times a matrix. So what we're going to do is we're going to go through and multiply each element of our matrix times that number. So in other words, just divide all the elements in the matrix by 11 in this case. So our top element will become negative 2, bottom element will become 8. So now our matrix equation is saying xy is equal to negative 2, 8. In other words, this is giving us two pieces of information. It's telling us x is equal to negative 2, y is equal to 8. And we have solved our system using the inverse matrix. So we could go back to our system and we could just double check if we put x equal negative 2 and y equal 8 in, works in the first equation, it also works in the second equation. So indeed, we have solved the system.